In this video, we'll be looking at another function related to the gamma function, which is called digamma. Digamma is an old Greek letter that isn't used anymore, but mathematicians usually use psi to denote this. It's the logarithmic derivative of the gamma function. Now, if we use the factorization of gamma from previous videos, we can write this in a more interesting way. So the factorization is 1 over gamma of z equals z e to the gamma z times the product of 1 plus z over n e to the minus z over n. Okay, so if we take reciprocals, we can then take the logarithmic derivative. So gamma is 1 over z e to the minus gamma z times the product of 1 plus z over n inverse e to the z over n. Now if we take logs, we get minus log z minus gamma z plus the sum. Now we have a z over n, and then we subtract the log of 1 plus z over n. Okay, now we differentiate, and we get gamma prime over gamma equals minus 1 over z minus gamma plus the sum of 1 over n, and then the derivative of log 1 plus z over n is, well, I have 1 plus z over n in the denominator, and then the chain rule gives me 1 over n. Okay, so this is the digamma function of z. I get minus 1 over z minus gamma plus the sum of 1 over n minus 1 over n plus z. Okay, so in particular, if I plug in an integer, a positive integer, most of the terms in this sum end up canceling. So I have a harmonic series, but I'm subtracting 1 over k, 1 over k plus 1, 1 over k plus 2, and so on. So what I end up with is really just the first k minus 1 terms of the harmonic series. So for integers, digamma of k is the k minus first harmonic number minus gamma. Okay, now one other interesting thing about the digamma function is that it's actually possible to get an exact formula for the digamma function of any rational number if you allow yourself to use this Euler-Mascheroni constant. So the reason for that is that if we go back to this formula, we can rewrite it in a way that lets us compute it more easily. So the trick is to notice that if you have 1 over a, you can write that as the integral from 0 to 1 of t to the a minus 1. Okay, that's pretty silly, but if we do that for this term and each of these terms, we end up with an interesting integral that we can compute for many values of z. So we end up with digamma of z equals the integral of minus t to the z minus 1, and then minus gamma, and then plus the sum of the integral of t to the n minus 1 minus t to the n plus z minus 1. Okay. Now, if we switch the order of summation and integration, which I won't justify here, we get minus t to the z minus 1 plus the sum of t to the n minus 1 minus t to the n plus z minus 1. And now this sum, if I factor out 1 minus t to the z, I'm just adding up t to the n minus 1. Okay, so that's a geometric series, so it's just 1 over 1 minus t. Okay, so altogether I get digamma of z equals negative gamma plus the integral of minus t to the z minus 1 plus 1 minus t to the z over 1 minus t. And the last step is combining this t to the z minus 1 into the fraction. So that gives me a minus t to the z minus 1 plus a t to the z. And that cancels with the t to the z that I had before. So I get 1 minus t to the z minus 1 over 1 minus t. Okay, now if I let z be any rational number, well, positive rational number, I can evaluate this exactly because with the substitution that integral becomes something I can do partial fractions on and evaluate in terms of logs and trig functions. So for example, if I want psi of a half, it's minus gamma plus the integral of 1 minus t to the minus 1 half over 1 minus t. And then if I substitute t equals u squared, I get negative gamma plus the integral of 1 minus 1 over u over 1 minus u squared times 2u du. And this is pretty easy to evaluate because it becomes 2u minus 2 over 1 minus u squared. And I can factor out a u minus 1. So I get negative gamma plus twice the integral of, okay, u minus 1 over 1 minus u squared. That's minus 1 over u plus 1. And that is just minus gamma minus 2 log 2. And similarly, I can evaluate digamma of any positive rational number.